Continuing the previous video, we start the second part of the quantum field theory from A to the Z. Today, first I will discuss the path integral formulations, and next I will turn to the loop integrations, and the renormalizations, and renormalization group, and the non-abelian group, non-abelian cases, and the anomaly or symmetry breaking. So in the previous we discussed the field quantizations and the Feynman diagram, but there are another formulation which is a path integral. There are some of the similarities in the statistical physics, so-called partition functions or generating function. We can define that as a partition function as a summation of all the Boltzmann's factor, and the ensemble averages can be obtained by the derivations of that partition function. All the endpoint correlation functions. Similarly, in the path integral formulations, we can define the generating function instead of the Hamiltonian, of the Hamiltonian density, which is the integrates over sort of the space-time, and similarly we can obtain the endpoint correlation function by an derivative sort of the generating function. So now, under such a generating function of formalisms is similar to the path integral formalisms in the quantum mechanics. Such a path integral formalism in the quantum mechanics, the amplitude from the initial state to the final state is can be obtained by the path integrations of the possible paths about the time evolution factors. And usually such exponential factors contains the quadratic terms, so this can be evaluated by the Gaussian integral. So this is a Gaussian integral for the e to the minus ax cube, which is a pi over the a list. And if there are the quadratic terms with the matrix form, this gives the determinant of the quadratic term matrix, and the linear terms are new. So for example, the first scalar field, this is a Lagrangian, and by the path integration to part, the kinetic term can be converted like that. And this is a quadratic term form, so the evaluation of this Gaussian integral gives such a form, root of one of the determinant of the a, where a is given by the partial squares plus m square. And if we evaluate the second derivatives of the such generating function, then we can obtain the two-point correlation function, which corresponds to the Green function of the propagator. So the second derivatives of the such a generating function yield the inverse of the matrix A, and this gives the propagators in the momentum space. Similarly, we can apply the path integral for the other spin, for example, the spinor field with the spin 1/2. In this case, the spinor fields are constructed by the Grossman number, and the Gaussian integral with the Grossman numbers yield that the determinant of the v, not in the numerator. So this is located in the not in the denominator. This is located in the numerator. So this gives the determinant b in here. So also this gives if we differentiate the generating functions with the second order, then this gives the propagators. This is the inverse of the b, which gives the propagators of the spin 1/2 field I over the p plus minus m. And similarly, we can obtain the propagator for the vector fields for the proper Lagrangian. This can be converted by the following quadratic term form. And the generating functional, and here's the propagator. Second derivative of the generating functional gives the inverse of the k, and the propagator to the vector field can be obtained. Here are some few theorems and remarks in the quantum field theory. There's Arasat reduction formula, which gives a relation between the S matrix and the endpoint correlation functions here. So this one is matrix line point cross a function of some other factor, and here's a proof. And such a Rashad production formula is used when there's a contraction between the external fields and the internal field. And there's also the word identity, which is the equivalence with the gaze invariance. So if there's some momentum factors are contracted with the amplitudes, then it is adjusted by the current contributions arising from the gauge symmetry. And also there are operator version for the Walter-Kazi identity. And the unitarity can be equivalent with the optical theorem. Unitarity instead of the S matrix means that S staggers and S equal to the 1. And if we decompose the S to the identity plus the amplitudes, then this gives this condition gives the imaginary part of M is equal to the M conjugate M, and so this gives the imaginary M gives all the possible summations of the M scarce with the intermediate states of the N. So that in the left hand side includes a loop level, but the right hand side includes a tree level, so the loop level can be decomposed by the two all possible intermediate states with the tree level case. Now we turn to the loop corrections. In the high order, the loop diagrams are possible, but such a loop diagram yield at the infinity, so we should regularize it. There are some of the many regularization techniques, but there are some evaluations methods for the products in the denominator, because in the loop diagram there's many propagators here, so this gives the products of the some propagator. So one of the A, B can be evaluated by the following integration, and we can define the loop momentum to make the quadratic form of propagator form for the such a multiplication term. For example, this is one example. Some of the propagator forms are multiplied, but this can be converted by the this care if we define the L scarce with L as a loop momentum, and the remaining terms can be interpreted by the mass pool. And there's several regularization technique to manage the divergence of an integral. The first one is the cutoff regularization. We can impose the cutoff capital lambda for the momentum. So this means that there will be the minimum lattice as a lambda inverse. And if integrate of the dp over the p to the cutoff lambda, then give the low divergence, which is the UV sensitivity. And also there are more technique dimensional regularization. We can assume that the space-time dimension as a d as some deviation from the ball, and we will go to the d to the ball limit as our universal space-time. Then there will be some divergence that can be appears as 1 over the epsilon, which equals epsilon go to 0. So this is a loop momentum. Already we can obtain such a form from the above the following identity, and this gives us such a form. And this gamma of the minus d over 2 has a divergence when the d go to the 4, so epsilon go to 0. So the divergence appears as 2 over the epsilon in here. And there is also a Pauli Bellas regularization. We can imagine the picture that we have in particular with the mass capital lambda, and this gives the precise sign of the kinetic term. And here are some few remarks. We use some regular tensions to make the space-time from the Minkowski speed to the Euclidean order plus sign for the space and the time component to evaluate the some loop momentums over the spherical coordinate. And there are some several renormalizations things, first for the build and the coupling and the mass. For the build case, from the free theory to the interaction theory, if the creation operators that acting on the vacuum state, interaction vacuum, then there will be the one particle state will be appear, but also the many particle states also will appear. And the such coefficients of the one particle state weight can be interpreted as a Biot strength renormalization. So if the Biot operator acting on interacting vacuum, then there will be the Biot strength renormalization through appears in the propagator. And the other term, the following many particle states can be expressed by the spectral decompositions correspond to the many particle state in here. So this is spectral density function correspond to the some capital M scale. So here's spectral decompositions as a representation of the spectrum. At the 4-amp scale, there are only one particle state, but from the 4-amp scale, there will be many particle states that correspond this here. And some width near the poles that correspond to the some imaginary parts of the pole correspond to the decay light in here. Next, I will turn to the mass renormalization, which arises from the electron surface energy in the QED process. For the electron propagator or fermion propagator, we can consider the loop integration from the following diagram. This is just a simple one loop case, and then we can calculate the this diagrams to the amplitude. For example, there is one fermion propagators and one photon propagators in here, and this by using the Byman identity and the evaluations through with the regularization techniques, and this gives a logo divergence in here. And if we as the order possible loop diagram, and there is a one pi diagram, so-called one particular divisible diagram, which means that the diagram cannot be splitted, and the order summations of the one pi diagram can be expressed by the geometric series. This gives the electrons mass renormalizations. So the renormalization mass of the electron mass is given like that, and here the delta is correspond to the counterterms in here. And similarly, such a one pair diagram from the electron surface energy also gives the building normalization for the electron build J2 as the numerator series coefficient for the propagators of the fermion propagator. So here is electron surface energy, and now I turn to the photon surface energy for the coupling constant normalizations. The one loop photon surface energy in the QED, the diagrams are following in here, and there are two fermion propagators in here, and also similarly we can use the Byman identity for the some several term the denominator, and by the regularization there will be the logarithm divergence will appear. And also there was a one pair diagram, and by using the all the possible diagram can be represented by the geometric series, and also we can bind the coupling or charging normalizations in the QED. And such a coupling has the dependence on the energy scale or momentum scale Q scale. This is called the learning coupling constants. And in the QED case, in the high energies, the coupling becomes strong, and in the bistructure level alpha, this can be represented as the following form. So at some specific energy scale, the coupling constant goes to infinity. This is called lambda form. And also there are another interpretation in the low energy scale. This corresponds to the long distance. So the coupling constant becomes small. This means that the interaction potential is also small. This means that the compolarizations of the electric dipole moment, which are arising from the vacuum energy, there are the screening effects of the electron and positron pairs from the vacuum. And I will turn to the binary topics in the QED loop. There's a vertex function which gives anomalous magnetic moment. Here is a vertex, and but we can also consider such a one loop level. Then there will be two fermion propagators and one photon, and similarly we can evaluate the amplitude by the Byman identity and the regularization. And such a product function can be represented by the two product form, one is the gamma mu and the other one is the sigma mu nu, by using the word and the Gordon identity. And the coefficient f1 up to is called the form factor, and this has some logarithm divergence by the regularization. First of the f1 corresponds to the electric charges, and the f2 corresponds to the magnetic field and the magnetic moment, and the combination of the f1 and f2 gives the anomalous magnetic moment, and such G factors arising from the anomalous magnetic moment can be tested in the one loop level, and in the QED case, this A, the deviation from the Z and the 2 is given by the alpha of the 2 powers. Alpha is the band structure constants of the QED. And so far we discussed the UV divergence when the momentum go to the infinity, but there is also the divergence in the IR implied level when momentum go to the zero, low energy scale. There is a Bloom-Sterling process, which is a radiative photon from the external electron line, and similarly we can evaluate this diagram with the additional propagator term. And for this, to legalize such divergence, we can introduce sort of the Wiktionary photon mass, even though the photons are massless particle, and this is double logarithms as a log IR divergence. And this means that the soft photons is not detected, and our regulators mean that the low limits of the detected as a resolution parameters in the experiments. And the double logarithm can be cancelled by the vertex functions IR divergence. So now we turn to the perturbative renormalization. So if we consider the loop level, then there will be always the divergence, and we should cancel the divergence, and such a cancellation of the divergence can be possible by the shifts of the several some constant like as a build master and the coupling, and before that the manage such a divergence from the loop level, we should count the how much divergence is here, and this can be possible by the degrees of divergence, counting the momentum boxes in the numerators and the denominator by using the loop and the electron propagator and the photon propagator, and this can be written by the other diagram informations like as external photon and external electron. So for example, in the photon self-energy, electron self-energy vertex function, which we discussed in the QED loop level, we can calculate the degrees of the divergence. Also, there are also dimensional analysis, the mass dimensions of the coupling constants. For example, if the coupling constant is positive, then this is super normalizable. But if the coupling is negative, this is a non-normal case, like the gravity theory. For example, the gravitational constant has a negative set of couplings in here. And depending on the space-time dimension, some couplings are normalizable, but some couplings are non-normalizable. Due to the mass dimensions of the couplings are different for the each dimensions of the space-time. For example, the pi systems, the C6 is that has a m2 minus 2 mass dimensions, so this is a non-normalization high dimensional operator. So now I will explain the main reasons of the renormalization. The renormalizations as the counterterm to remove the divergence, and this shifts the other parameters. So for example, there will be some observable, some capital O, and arising from some coupling lambda, and in the loop level there will be some divergence terms as a logarithm form, and we can impose the renormalization condition at some scale q0. The observable is the same with the lambda 0. And to remove the divergence, we can add the counterterm delta lambda. Then to remove the divergence, such a lambda term can be rewritten by the renormalization condition things, and this gives also the parameter shifts and the cancellations of divergence by adding the counter term. And there are several possible algebra schemes how much the finite part is absorbed in the counter terms. So when the some divergence past this exactly cancels out. The first one is the onshore scheme, the poles that appears at the momentums correspond to the pole mass, and in this case the p scales exactly same with renormalizes the masses. But there are also some MS scheme, minimal subtraction scheme for the dimensional regularization, and in this case in the dimensional regularizations is one of the epsilon form, and the counter terms only removes such one of the epsilon term. The MS var scheme or the term like the minus gamma plus log of 4 pi is also the cancelled. So there's one example for the Piper theory counter term renormalization. There is a paired Lagrangian, and if we rescale the build to the field renormalization, there is some rescale Lagrangian, and this can be decomposed by the physical term and the shift sum with the counter term. So there's parameter shift for the build, mass, and the coupling. And the both such a counter term delta j delta m delta lambda. Also we can find the Feynman rule for such a counter term. And the counter term can be determined to remove the divergence part. So for example, the delta m's to delta m is determined to cancel the such one of the epsilon divergence in here. And there's the QED normalizations as the second example. There will be the three rescaling bit electron, electric charges, and the fermions, and the Bakht-Gauss boson. So here's a paired QED normalization and the rescaling with the Z1, Z2, Z3. And there are such a rescaling fields that decomposed by the physical and the shift part. And the counter term can be determined to cancel the divergence and impose the renormalization condition. So there's a proton self energy, electron self energy for Tux function as one of diagram QED process, and we can determine the counter term for the delta 1, delta 2, and delta 3 for each cases. So the delta 1 corresponds to the electric charges, delta 2 corresponds to the electron mass, and the delta 3 corresponds to the proton build renormalizations in here. So now turn to the Wilson renormalization group. And as a result of the renormalization, the parameters are shifted and it gets the energy scale dependence. So we can transform from the low energy to the high energy. This is called some RG equation. And we can impose some with the cutoff, which is called effective theory EFT. So from the lambda to the v lambda, where the b is smaller than the 1, then we can transit from the high energy to the low energy. So the best mode integrates out. Yeah, the best mode pi epsilon integrates out. Only the slow modes remain. And the higher dimensional operators are suppressed out already with that. So for example, the ball palm theory is in the wave interactions. If in the low energy, the high energy W heavy mass W that the bosons are integrated out. So only the W scales remains in the propagated in the low energy limit. So this keeps the parameter constant, and the similar for the neutrino. These relations arise as having neutrinos masses are integrated out. And also for the barrier number of relations in the photon decay in the GT model. And we can also consider the RG renormalization group, the code of change transformations continuously. Although some of the coupling the scale dependence as a learning coupling, but the observable part like the Lagrangians and the amplitude scales are scale invariant. So the such as endpoint correlation functions are scale invariant. So the differentials of the energy scale this is equal to 0, which gives the Kalan-Samanzik equation. And you can define the beta function, beta z, as a coefficient of the Kalan-Samanzik equation. And another coefficient of the Kalan-Samanzik equation is the anomalous dimension as differentiations of the renormalization chart about the energy scale. For example, the pipe theory in here, we can find the anomalous dimensions gamma and the beta function betas by evaluating G2 and G4 and the differentiation by the Kalan-Samanzik equation. Also for the QED level, there will be the two anomalous dimension and the one beta function. This corresponds to the electron and photon respectively, and the beta corresponds to the electric charge, and we can obtain the similar results of the learning coupling constants by this beta function. And instead of the evaluate the exact solutions of the beta function, we can also find some qualitative behaviors of the coupling by using the renormalization group law. There will be some fixed points, which is a beta function exactly vanishes at some space. It is in this case invariance around this point is called a fixed point. And we can linearize the beta function near such a fixed point fp. And depending on the scalar dimension sign, some coupling is relevant, but some points are relevant. And also the marginally fast remain, but it should be the higher the tucking is necessary. For example, the equal for scalar field theory, we can find the fixed point, trivial one, and with some Fisher pointed. And in this case, this is the RG flow for the G24 in the scalar theory. G2 corresponds to the quadratic term coefficient, and the G4 corresponds to the chaotic coefficient term. And for the non-trivial Wilson pressure fixed point is in the G4 directions, the G4 are irrelevant, for the G2 directions are relevant. Increases when the G2 increases. So now it starts about the Young's theory, non-abelian case symmetry. In the QED, we only discuss the U1 symmetry, and this is the commutatives or abelian, but there are other SU2 and SUN such a theory to express the standard model of particle physics. It includes the non-abelian theory, which is the non-commutative, and this can be represented by the Lie group and Lie algebras and the commutative relations of the generator. And there are some definitions of the partial orthogonal group as so on, and the partial interactive group as U and the for simple example of the SU2 and the SU3. We only focus on SU2 and SU3 because the standard model includes such a gauge symmetry. And for such a Lie group or continuous group, we can find the representation theory of the generator. The dimensions of the groups are given by the number of the generator, but dimensions of the representation are given by the size of the matrix, and depending on the such a two kinds of dimensions, we can find the two kinds of representations of the Lie algebra. The first one is a fundamental representation, which is the minimum. The dimensions of the groups are same to the number of the generator, but the dimension of the representations is n for the SE, and so this is the minimal case. But the adjoint representation is the second kind. The metric representations of the generator is given by the this constant FABC, which are from the commutative relations of the generator in the algebra. And in this case, the dimensions of the matrix for representation of the generator is the same with the number of the generator. So the dimensions of the representations is the same with n squared minus 1. The number of the generators is n algebra is n squared minus 1. And we can find the Casimir operator, which is the commutator with the order operator, T square. And the quadratic Casimir defines as the proportional coefficients for such a Casimir square operator, and the index of the representations that defines as a traces of the such a form. So C2R quadratic assimilated TR index can be determined by the following identity. So the TR and the C2Rs arises when we evaluate the structure constant in the some non-abelian gauge symmetry vertex. And there is also some advanced topic with another Wilson loop as a geometry version of the gauge theory. We can consider the Wilson line to connect the different space-time x and y. This Wilson line is a bilocal field, and transforms by the following relations under the gauge symmetry. And such a Wilson line can be obtained by the exponentials of the integrations of the gauge field. So the gauge fields correspond to the connection between the two space-time. And by using the Stokes theorem, we can find out the width loop. And this A mu is an exponential factor, it becomes a field strength F mu. And we can find the covariant derivative d mu with the connection. So the covariant derivatives includes the connection gauge field, so the interaction terms are included. And the field strength can be obtained by the commutatives of the such a d mu and the d nu. This is a similar reason for the Riemannian curvature tensors in the general relativity theory. So now we are prepared to the consider Yang-Mills theory of the non-abelian gauge symmetry. Here is the non-abelian theory. Covariant derivative now includes the generator and the vector gauge boson. There will be the bunches of the generators in here because it's a non-abelian theory. The field strength also now includes the non-commutative term in here, including the FABC structure constant. So it includes also the non-commutative terms for the gauge bosons and the base strength. So the interacting part now includes the non-commutative term, partial A term with the coupling with the F, and the Bohr gauge boson coupling with the F and F, such a two form, Stiglitz-Lorenz Bohr-Coulomb vertex. And also there are some advanced topic. In the non-abelian theory, we should always consider the Butterfield's proof of ghost. Originally, when we consider the first integral formulation, there was a gauge fixing term, J term, QC. Also similarly, there is Yang-Mills gauge theory. There will be the anti-commuting ghost colors will appear. There is also a gauge fixing term and the ghost term. And now we can evaluate the QCD normalizations for the 3 vortex and 4 vortex, which are arising from the non-commutative term and the ghost field. And such evaluations are possible by the quadratic coordination and the index of the representation. And we can find the Vela function for the QCD coupling. And by the number of the generation, the number of the colors and the number of the generations in the clock, such a beta functions becomes a negative. This means that in the QCD non-abelian group, the couplings becomes small when the energy go to the high. So this is called the asymptotic freedom. And for the small distance, the low energy and the long distance, the coupling constant become large. This is called the color confinement around the screen. The previous opposite with the QED. The final topic of the contemporary theory is the symmetry and its making. First of all, in the QCD, there will be the QCD some breaking scale, and above that there's a QCD, but below that there will be the chiral perturbation theory. So the below sort of the such a QCD scale, the quarks are confined, so it is forms the baryon of the meson. And this meson builds can be obtained by the color perturbation theory as effective field lithium. So with the color perturbation Lagrangians, the delta includes the meson boom with the generator. So for example, if there is a UDS 3 flavor, then the pion K meson can be obtained this, and the mass of the pions and the kaons can be obtained by the relation between the up down strange quark mass. This is called the German mass relation. And the binary fixed anomaly, the classical symmetries are destroyed by the quantum loop effect. In this case, the world cast identities are broken. For example, is compared between the vector and the color symmetry. If we consider the triangle diagram, then all the physical methods for the path integral measures are not invariant as color symmetry given A. Then the word identities are broken. There will be always anomalous term. So classical symmetries are broken, but it's a total derivative term. So that does not change the perturbative calculation. And there's a testing index theorem, such a topological term can be converted to the algebraic term corresponding to the integer number. The integrations of the f tilde was the f tilde as a dual spell strength. It gives the differences of the integer number correspond to the sum Chern-Simons number. And there are several types of anomaly. Originally color ABJ anomalies consider two gauge field, gamma gamma, and one globe field correspond to the pion. But there is a Tufts anomaly, 3 global symmetry, and gauge anomaly, 3 gauge symmetry. For the gauge anomaly, they should be always cancelled in the standard model, and to cancel the gauge anomaly, there will be the SS3 and ST1 charges in the standard model, and the charges of the Kirk, Lupton, Higgs field should satisfy some specific relation. So, for example, you want to have a charge, all the fermions are relevant, but the SS3 with the Kirk or ST2 left-handed ones are relevant, and the gravity also relevant, and the standard model charges satisfy the such gauge anomaly cancellation. And if we add additional gauge symmetry like the U1 P minus L prime, that should be also the anomaly free, and the additional U1 prime charges for the fermion field should satisfy the additional anomaly cancellation condition. So we discussed the quantum field theory from A to the